I welcome my viewers and students to this lecture on mass spectrometry. Mass spectrometry is a technique that involves the bombardment of molecules of a compound in the gas phase with a beam of high-energy electron, usually about 70 electron volts. The process, known as electron impact, EI, may knock off an electron from a sample molecule to produce a molecular ion N+ of high energy. It helps identify the amount and type of chemicals present in a sample by measuring the mass to charge ratio and abundance of gas phase ions. It provides information on elemental composition, molecular structure, and quantity achieved by ionizing a sample, separating the resulting ions in electric magnetic fields and detecting them. It works by converting molecules into gas phase ions, fragmenting them, sorting these fragments by their unique MZ, and generating a mass spectrum intensity to reveal the sample's chemical fingerprint, crucial for fields like medicine, chemistry, and environmental analysis. For this lecture, we will be considering the mass spectrum of two alkanes. What are the common types of mass spectrometers? We have two types, GCMS and LCMS. The GCMS is called the gas chromatography mass spectrometry. It's a technique that combines the separation power of gas chromatography, GC, with the identification capabilities of mass spectrometry. GC part separates the component of a mixture based on their boiling points and affinity for the stationary phase, while the mass spectrometry part, the MS part, ionizes the separated compounds and detects them based on their mass to charge ratio, MZ, M/Z, used for identifying and quantifying volatile and semi-volatile compounds. Analyzing complex mixtures, for example, environmental samples, drugs, fragrances, etc. It is very useful for forensic and pharmaceutical applications. The LCMS is called the liquid chromatography mass spectrometry. It is a technique that combines the separation power of a liquid chromatography, LC, with the identification capabilities of mass spectrometry, MS. LC part separates compounds based on their interaction with a liquid mobile phase and a stationary phase. The mass spectrometry part ionizes the separated compounds and detects them based on their mass to charge ratio, M/Z. It is used for analyzing non-volatile compounds like peptides, polar and thermally unstable compounds, biomarker discovery, and metabolomics. Very used for detecting and quantifying compounds in complex mixtures like blood, urine, and food, etc. The figure 1 shows the mass spectrometer. In the mass spectrometer, we have this sample, and then we'll have the gas sample injection point. From that injection point, we introduce the sample, and then we have the sample vaporizer, which is the heater, and then there is an electric beam that is also there in the spectrometer that helps in the acceleration of the ions. The ions will now be accelerated, and then there is a magnet. On that magnet, it shows the positive and the negative part of the magnet. The ions on the negative charge ions will be lost in the process of the mass spectrometer, while the positive ions will be the one that will be detected. The magnet has its own magnetic field are shown, and then it moves to the detector. Ionization. The sample can be a solid, liquid, or a gas, and is converted into gas phase ions, often by bombarding it with electrons, which can cause molecules to break apart. That is, fragments. In the mass analyzer, the molecular ions are energetically unstable, and some of them will break up into smaller pieces. The simplest case is that a molecular ion breaks into two parts, one of which is a positive ion, and the other is an uncharged free radical. As shown, M dot plus will give us S plus Y negative, or Y dot. The uncharged free radical won't produce a line on the mass spectrum. Only charged particles will be accelerated, deflected, and detected by the mass spectrometer. These uncharged particles will simply get lost in the machine. Eventually, they get removed by the vacuum pump. The ion S plus will travel through the mass spectrometer just like any other successive positive ion, and will produce a line. On the stick diagram, all sorts of fragmentations of the original molecular ion are possible, and that means that we get a whole host of lines in the mass spectrum. Each kind of ion has a particular ratio of mass to charge ratio value. For most ions, the charge is 1, and thus the MZ ratio is simply the molecular mass of the ion. Lighter ions deflect more than the heavier ions. The molecular ion is often given the symbol M plus or M dot plus. The dot in this second version represents the fact that somewhere in the ion there will be a single unpaired electron. That's one half of what was originally a pair of electrons. The other half is the electron which was removed in the ionization process. A detector counts the ion at each mass to charge ratio, creating a mass spectrum that shows the relative abundance of each ion. A mass spectrum is a plot of relative abundance against the ratio of the mass to charge ratio. These spectra are used to determine the elemental or isotopic signature of a sample, the masses of particles and of molecules, and to elucidate the chemical structures of molecules and other chemical compounds. Why these peaks? Interpreting the mass spectra. There are key steps. 1. You identify the molecular ion, that is the M plus ion. Look for the highest MZ value, may be small or absent. Then you confirm molecular weight. 2. You look for fragment patterns. For an alkane, you look for the loss of 14, which is a CH2. You can also look for the loss of a CH3, which is 15, showing the cleavage of a branch alkane. And you look for C2H5, molecular mass of 29. That is the production of secondary propyl cation, which can give an MZ of 43, etc. For alkenes and alkynes, you look for the loss of 27, which is C2H3. And then you can look for the loss of 41 also, which is C3H5. For aromatics, number 3, for aromatics, you look for the loss of 77 and the loss of 91, trophylum. You can also look for carbonase, the Mark-Lafferty alpha cleavage. you check for isotopic patterns. You look for chlorine, bromine, M+2 peaks. You look for sulfur, M+2 at 4% of M. And then you look most stable fragment. That is number 4. You look for the most stable fragment. Often tells you about the structure. And then 5, you combine with IR, NMR for full structure identification. Mass spectra alone cannot interpret the spectrum. You must combine it with the IR, infrared spectrometry, and then the nuclear magnetic resonance for full structure identification. Let us use the example of a simplified mass spectrum of pentane. The mass spectrum of pentane shows several peaks at 72, 57, 43, and 29. The molecular ion Mz is 72, which shows the total molecular structure ion of pentane, CH3, CH2, 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 CH3. If we add all together, we will have 72. And that is the line produced by the heaviest ion passing through the machine, which is pentane. It will now fragment into different other ions. And then in the fragmentation pattern, we are seeing a peak at 57. The peak at 57 shows a butyl cation formed, C4H9, and the loss of a methyl radical. And that methyl radical produced will simply get lost in the machine. We see another peak at 43. And that peak is the most intense peak, the MZ43, which is called the base peak. It is the longest peak. It is a propyl cation being formed by the loss of an ethyl radical from the molecular ion. It is usually given an arbitrary height of 100, and the height of everything else is measured relative to this. The base peak is the tallest peak because it represents the commonest fragment ion to be formed, either because there are several ways in which it could be produced during fragmentation of the parent ion, or because it is a particularly stable ion. We have another MZ at 29, which forms the ethyl cation. The ethyl cation is being formed at MZ29. And then we are seeing the loss of a propyl radical there. So it is important that we know the cations that will be formed and the radicals that will also be lost in the course of writing our equation in the mass spectrum. Let us look at another example, the mass spectrum of hexane. In the mass spectrum of hexane shows several fragmentation patterns. It shows an M+1 at 86, which is the molecular ion that represents the intact hexane structure, intact hexane molecule, though it is often low in abundance due to easy fragmentation. We saw another peak at M71, though not very much, that could represent the fragmentation pattern of a pentyl cation formation and the loss of a methyl radical. We'll have a prominent peak at MZ57. MZ57 there shows is the longest peak, and it is called the base peak It is the formation of a butyl cation and the loss of an ethyl radical. We have another peak at MZ43. The MZ43 produces a propyl cation and a propyl radical loss. And then we'll have the peak at 29, which is showing the fragmentation to an ethyl cation being formed and the loss of a butyl radical. It is always important that you indicate where the positive and the negative and the radical will be in your equations. What are the applications of mass spectrometry? Mass spectrometry is used for environmental monitoring and analysis. Soil, water, and air pollutants can be analyzed using the mass spectrometry. It is also used for geochemistry, age determination of soil and rock, oil and gas surveying. It is used in the chemical and the petrochemical industry, very, very important for quality control. Very important in the identification of biomolecules such as carbohydrates, nucleic acids. It's also used for proteins and oligosaccharides, sequencing biopolymers. Used for the determination of the molecular mass of peptides and proteins. Is used for the monitoring of gases in patient breath during surgery. Is used for the identification of drug abuse and metabolites of drugs in blood, urine, and saliva. Also useful for analysis of aerosol. Useful for the determination of peptide residues in food. Is used for isotopic analysis, that is, identifying different isotopes of elements. Useful for the determination of unknown compounds and analyzing complex mixtures. And it is very useful for quantifying the amount of known substances, etc. Study questions. We have 4 study questions here. 1. Predict the mass spectrometry of butane. You go online and download the mass spectrometry of butane, and then you explain the different formations of the MZ ratios or ions. And then the second one, predict the mass spectrometry of heptane. 3. Describe the mass spectrometry technique. And 4. State the differences between the GCMS spectrometry and the LCMS spectrometry. Thank you for watching this video to the end. See you in the next class.